Hi all, how are you? I hope you enjoy your weekend. If you can hear me, please thumbs up in the announcement I just made in the chat. Okay, thank you so much. I see you can hear me. Okay, so today we are going to continue with the topic we started last week around arithmetic for computers. Before starting, I would like to show you, I have made an announcement and I have also and I wanted also to mention it here so you can see on the Canvas page that last week, lecture 6, there were some errors. So you have here exactly in which slides there were errors. I have updated those slides. I have also added comments on the videos. But yes, just to be sure that all of you know that there were a couple of errors. Thank you thank you to the ones that spot them. And yeah, if you see additional errors, just let me know. I also did another announcement which was regarding the main rep. So remember, this module has a main rep, which is the one you see in this announcement. I think it's pronounced Kalem. And yeah, so if you want to send some feedback, so you can send it to the main rep, and yeah, that was what I wanted to comment. Okay, so let's go back to the lecture then. So today we are going to see binary multiplication and binary division. Remember that in the last lecture we saw addition and subtraction. Today, multiplication and division. So let's start then with the multiplication. First of all, we will assume that in binary we just multiply numbers like in decimal numbers. So for example, let's say that we have this multiplication. Imagine that we want multiply 100 by 101. So this will be the binary value. This will be the equivalent value. On the right side, we have the equivalent value in decimal. So if we want just to multiply this number in binary using the same method we use in decimal, we just will be multiplying. First of all, we will multiply 1 by the multiplicand. Okay, that makes this number 1000. Then I will go for the second digit of the multiplier, which is 0 in brown, and I will multiply this 0 by 1000. It's 0. Then I will go to the third digit, which in green, which is 0 again, and then I have 0 again. And finally, I will multiply the last digit, which is 1 in yellow by the multiplicand. So in the end, I will have all these numbers, which I will just add, and I will have those numbers here. Okay, this will be the result. In this case, the carry is 0. And in order to check the product, I can do, as always, check it with the decimal operation. And in this case, we see that this result matches the binary and the decimal. Okay, makes sense? This is just what you do with decimal numbers. So now I would like that you do this multiplication. I have a form, and I'm going to share with you the link to that form. And similarly to what I have done in the previous slide, I just want you to do that multiplication. Okay, so you can see the link to the form in the chat, and I give you 2 minutes for this. Okay, so thank you very much. I think that most of you got the what seems the correct answer. Okay, so let's see how this is done then, similarly to what we have done with the previous one. So again, we will start by multiplying number one, the first digit, by the multiplicand. This gives us this value. Then we will follow with the second digit in brown, which gives this value. Then we will continue with the green one, which in this case is 0, and the yellow one, which is 0 again. And then we will just add all those values, and then we will check the result again in decimal. Okay, so I think this is clear, this is easy. So let's turn now to something a little bit more complicated. So for humans, this is an easy way of multiplying numbers, but when we want to implement this in a machine, we need to complicate this a little bit in order to make it easier for the machines, but complicated for humans. So the algorithm we are going to use initially for doing the multiplication is the one you see in the screen. So in the first part of this algorithm, in the top part of the algorithm, we just start the algorithm, and then the first thing we do is we test the first digit of the multiplier. If the first digit is 0, we don't need to do anything, because if we multiply something by 0, we know the result is going to be 0. And on the contrary, if the first digit of the multiplier is 1, what we do is we add the multiplicand to the product and place the result in the product register. We will see later how this is implemented in hardware, and we will also see an example. So just try to be with me during this algorithm slide and the following one, and then once we see the example, everything hopefully will make sense. So this will be the first part of this algorithm. Then once we have done that, we just go to the second step, which is we shift the multiplicand register left 1 bit, and then the third step is shifting the multiplier register, in this case right instead of left, 1 bit again. And this algorithm is designed for leg V8, and in leg V8 you know that register has 64 bits. So in this case we assume that we are going to have 64 repetitions for this multiplication. Okay, because the inputs will be 64 bits registers. And then once we have done this 64 times, we are done. Okay, if you don't completely understand it right now, don't worry. So in the next slides, you will for sure understand it. So as I have mentioned, regarding the numbers of repetitions of this loop here, of those three steps that I have mentioned, it depends on the number of bits of the multiplier, and in this case we assume that the multiplier has 64 bits because it's the length of the registers in leg VI. So let me show you now how this algorithm is translated to hardware. So in this case, when we want to translate this to real hardware, we have this circuit. So first of all, we have here the multiplicand, 64 bits. And then this is the first operand for a 64-bit arithmetic logic unit. Remember that this kind of unit can, for instance, do addition. So in this case, we will have this first operand, and the second operand will be the register, which in this case is product, that initially is initialized to 0. And here we have the multiplier. So here we have like a control unit which will decide if we need to perform the operation or no. Remember that if the bit we are the algorithm says that if the bit we are if the bit of the multiplier we are considering is 0, we don't need to do any operation. So the control test here will say, okay, don't do any operation if the multiplier digit we are considering is 0, and if it's 1, it will do the operation, which is adding the multiplicand to the product and place the result in the product register. Now we can see the product register. Okay, and this control test will also indicate when we need to shift left the multiplicand, which is the second step of the algorithm, or when we need to shift right the multiplier, which is the third step of the algorithm. Okay, so this will be done 64 times, and in the end we will have here in the product register the result. So let's do an example using this algorithm. Instead of doing it like before, we have done this using the way that humans use to multiply the numbers. Now we are going to try to use this algorithm. So here we have the initial values. So then first we check the first digit of the multiplier. We see that it's 1. So if this number is 1, what we have mentioned that we need to do is add the multiplicand to the product and place the result in the product register. So this addition will be done by the arithmetic logic unit. Okay, so we have basically we have add the multiplicand, this number here, to the product, and we have placed the result in the product register. So this is actually this operation, product equal product plus multiplicand. Okay, the number, the register we change is the register in red. So the next step will be then shifting the multiplicand register 1 bit left. So this register here, we shift it 1 bit left to the left, and we introduce a 0 then in the first in the rightmost register. The second step will be shifting right the multiplier. So the multiplier was this number, and now is this one. We have shifted it right and placed a 0 in the leftmost side bit. Okay. And then again, we repeat the same process again. So we check the first bit of the multiplier and we see, okay, it's 1. So what we do is adding the multiplicand to the product and place the result in the product, which is actually what we have done here. We have added this number to this number and place it here in the product. Then again, we shift left the multiplicand, we have done here. And then again we shift right the multiplier and repeat again the same algorithm. So in this case the digit we are considering for the from the multiplier is 0, so we don't need to do any operation. We just keep the value in the product. We shift left the multiplicand as always, and we shift right the multiplier and check the value, and again is 0, and if it is 0 we don't need to do any operation. We just continue the algorithm, shift the value of the multiplicand left 1 bit and right the multiplier, and then in this case the multiplier has 4 bits, so we only need 4 steps. If the multiplier has 64 bits, we will need to do 64 steps like the one we have done. So here we only need 4 iterations. If the multiplier has more bits, we need to do as much iterations as the multiplier, as the digits of the multiplier. Okay. So if you review now the algorithm we saw before and the hardware, I think you will understand now why we use this algorithm for the machine, because it's very easy for the machine to perform this kind of operation. Okay, so now I would like that you do something similar to what I have done here, but using a different operation. Okay, so you have here the multiplier, the multiplicand, the product. You can see here the algorithm, and I want that you do something similar to what we have done in the previous slide. Okay, so I'm going to give you, in this case, 5 minutes to do this, and the time starts now, and we will check later the result for this operation. Okay. Okay, thank you. So the time is over. Hopefully you had time to finish it. So now we are going to see the solution. It's similar to what we have done before. Okay, so we just have those initial values. We check the first bit of the multiplier. The first digit is 1. So then if it is 1, the algorithm says that we need to add the multiplicand to the product and place the result in the product. This is actually what we have done here. The next step is shifting left the multiplicand as we have done here. Next step is shifting right the multiplier as we have done here. And then we check again the digit, the first bit of the multiplier, and then everything is repeated as before. So you have here the result. I think that this is clear, and you have the slides, and yeah, I don't see any problem in doing this. It's just repeating the same algorithm again and again, and we stop at the fourth iteration because, as we have mentioned, we need as many steps as the multiplier, as the bits in the multiplier. So in this case, the multiplier has 4 bits, so that's why we stop at iteration 4. Okay. When we go to leg V8, we have, for multiplier, we have the following instructions. So to produce a properly signed or unsigned product, leg VI has 3 instructions. The first one is multiply, the one you see in the screen. Then the second one, this multiply just gives the lower 64 bits of the product. If we are in leg VI, if we are multiplying 2 registers, it will be 64 bits by 64 bits. The result will be 128 bits. So we will need 2 registers. So the multiply one will give us the lower 64 bits of this product, and for the higher part, it will depend if the multiplier and the multiplicand are signed or unsigned. If they are signed, then we use the signed multiply high for this upper 64 bits of the product, and if not, we use the unsigned multiply high. Okay, so this is this will actually do what we have done by hand. It will be done by this, something similar will be done by this operation. A bit more efficient and optimized, but something similar. Okay, so now we are going to see something similar, but for the division. So we have seen multiplication, and now we are going to see something similar for the division. Just one thing more, so you can see here on the top the format of this instruction is an R format instruction, such as the one we have seen for add or sub. So it's the same as always. I don't see any problem here. I think you have the knowledge for using those instructions, and you have also them in the reference data. So yeah, I don't see any problem here. But if there is any problem, just let me know, please. So let's change now to the division. Similarly to the multiplication, for the division, we can do just like we divide decimal numbers by hand. So for instance, let's do this example with this dividend and this division. So first of all, we just multiply the division by 1 and see that we have 1 as a remainder. Then we cannot multiply any value by 1000 to be subtracted by 1. So we need to add down a 0 here. Then and put 0 there. Then again, there is not 10 is smaller than 1000, so we need to go for the next number. We down 0 again, and then finally, now in this case, we see that 1000, we can multiply this by 1, and then we will have 1000 here, and if we subtract this, we have 0 as a reminder, and this will be the result. Again, for checking this result, we can just use the decimal operation just to check that it's correct. Okay, if you see, so in the multiplication we were just using add, and in the division we are just using subtract. Okay, so that means that in terms of hardware or arithmetic logic unit, we'll only need add and subtract in order to actually perform an operation, a multiplication or a division operation. Okay, so now again, similar to what we have done with the multiplication, I would like that you do the same, but with a different value. So for instance, I have this exercise for you. Again, I'm going to give you a couple of minutes, and I'm going to give you a couple of minutes, and I will add in the an announcement with the link to the form. Okay, so hopefully you had time. Let's see. So this is the answers. Most of you got the right one. Okay, and again, we are going to see the result. So similarly to before, in this case, it's very easy. We just multiply the first in the first term 1 by this the divisor, then we put the divisor here, we subtract it, and we have the remainder is 0, and in this case we are just having all zeros, and the remainder is 0, and the quotient, the result, is 1000, and we can check this with the decimal operation, and yeah, great. Okay, I think this easier. So now let's do something similar to what we have done with the multiplication. So this is the way humans will divide. By the way the machine is going to divide will be different. So in this case, we have this algorithm for the division, similar to the one for the multiplication. And the reason is again the same, that for the machine, it's easier to use this algorithm given the properties and that the circuits has for the machine. Okay, so the first part of the algorithm is just this. For us humans, we just check if the divisor and the dividend are equal, or we in order to place a 1 or a 0. In this case, the machine actually what happens is that he subtracts the divisor register from the remainder, and in the remainder is initialized with the dividend and place the result in the remainder. So if the remainder is positive, it means that it was okay, but if it is negative, it means that it was not okay. So let's go for the easy part. So if the remainder is positive, then we just shift the quotient to the left and set the rightmost bit of the quotient to 1. If the remainder is negative, we need to undo this operation. So we need to add the divisor that we have subtracted here. We need to add it in order to left the remainder, to restore the remainder. Okay, and after doing that, what we do is we set the rightmost bit of the quotient to 0, and then we continue with the next part of the algorithm. So in this case, the third step will be shifting the divisor register right by 1 bit. And notice here that in the multiplication we needed 64 repetitions because we were multiplying registers of 64 bits. In this case, we need 65 repetitions. Okay, so the number of repetitions in this case is equal to the number of bits of the divisor plus 1. With the multiplication, we only needed the number of bits of the multiplier, but in this case we are adding 1. Okay, in this case it will be for 64 bits register, we need 65 repetitions. So the hardware equivalent to this algorithm is the one you can see here in the screen. It's similar to the one we have seen in the multiplication. We have the divisor here. Initially, we set the remainder with the dividend, and we have here the quotient, and again we have a control unit here which tells us when do we need to write the remainder or not, when do we need to perform here an operation or not, when do we need to shift the divisor right, when do we need to shift the quotient left. Okay, so let's do as before. Let's do an example, and with this hopefully it will be much clearer. So for instance, let's assume those values here. So then what we have done here is just subtracting the remainder, the divisor from the remainder, okay, and we get this result. What happens is, assume that we are using a choose complement notation. So if we have a 1 here, it means that the number is negative. So if it is negative, the algorithm says that we need to restore the remainder. So the remainder initially had this value, and we need to restore it to this value. For restoring it, we just undo the operation we have just done. If before we have subtracted the divisor, now we are going to add it again. What we need to do then? We shift to the left the quotient, which is what we have done here. And then we shift right the divisor. Okay, and in the case of the quotient, we have shift it left and adding a 0 in the rightmost significant bit, if I'm right. Okay, so now we go again for the next step. In this case, we do the same. We subtract the divisor from the remainder, and in this case it's positive. Why? Because we have 0 here. So if it's positive excuse me, if it is positive, then what we do is we shift the quotient left, but in this case we add a 1 instead of a 0 like in the previous example. In this case we add a 1. Okay, and then we shift right the divisor, and again we do the same. We subtract the divisor from the remainder. In this case we have here a 1, so it's negative. we undo what we have done, which means we need to add the divisor again. We shift left the quotient, placing a 0 in the rightmost bit. We shift right the divisor, and we continue in the next slide. Okay, this is the step, the iteration we have done. And again, we do the same. We subtract the divisor from the remainder. In this case, it's negative again, so we need to undo this operation. So we need to add here, we add again the divisor. We shift left the quotient and add a 0 in the rightmost significant bit. We shift the divisor to the right, and again, the next step, we subtract the divisor from the remainder. In this case, we see that it's positive, so we shift left the quotient using a 1, and we shift right the divisor. And remember, we are using the dividend has 4 bits, so we are doing 4 plus 1 steps. Okay, so in this case it's 5 steps and we finish, and this will be the algorithm. Okay, so now what I would like is that you do the same, but using different numbers. Okay, so I give you again 5 minutes for doing this. Okay, and the time starts now. So you need to do what we have actually done with in the previous slides with the other values, but this time with new values. Okay, so the time has finished. So let's see now the solution to this exercise. So then, as before, we have those initial values. So what we do first is just subtracting the divisor to the remainder, and we have this value. As we have a 1 here, this means this number is negative, so we need to undo this step. So for undoing this step, we add the divisor to the remainder, and we just restore the value to its initial value. And then we shift the quotient 1 bit left and add a 0 in the rightmost significant bit. Then we shift the divisor right by 1 bit. So the divisor here is shift right. That will be the first step. Then what we do is, again, we subtract the divisor from the remainder, and it gives us this value. In this case, the first bit, the left most bit is 0, so the number is positive. So then what we do is shifting the quotient left, but in this case we add 1. So this is the difference. When we have a negative value, we restore the remainder, and we add a 0 in the rightmost significant bit of the quotient, and if it's a positive number, we add a 1. Okay, so in this case it was a positive number, so we add a 1, and then the remainder is 0. Then we shift right the divisor, and we do again, so we subtract the divisor from the remainder. It's a negative value, so we undo that operation by adding again the divisor. This is what we have actually done here. We shift left the quotient. In this case, we add a 0 in the rightmost significant bit because the number was negative. This is indicated by this bit 1 here. And then we shift right the divisor. We continue in the next slide. Okay, this is the step we have just done. Then for the fourth iteration is the same. We subtract the divisor from the remainder. The value is negative, so we need to undo this operation by adding again the divisor, which gives us the same values that we have initially. We then shift left the quotient, and we add a 0 in the rightmost significant bit. We shift right the divisor, and we add we just shift right the divisor. And finally, the last step, we do exactly the same as in previous iterations, and we finish in this 5 step. Okay, because the dividend had 4 bits. Okay, so we will see. Don't worry, we will see more examples like this in the lab for this part of the module. And it will include doing more operation like this one. So what I want to show you now is how we do this in LegVI, similar to what we have done with the multiplication. We have an R format instruction. In this case, we have sign divide and unsigned divide. So depending on if the operands are signed or unsigned. Okay. And yeah, so both instructions in this case ignore overflow and division by 0, so the programmer needs to take this into account. Okay then, so we have seen multiplication and division today. With that, we have addition, subtraction, multiplication, and division. And in the next lecture, we'll just review the floating point standard, which you have actually seen, but I would like to review it in order to use it in the next lectures. Okay, so let me see if you have any question I can address now. So someone is asking saying that you have used another way for doing this kind of operations in the network part. So I'm happy to use any operation. I'm just showing this operation in the context of computer architecture because that makes easier for me later to explain how the machine is actually doing this. Okay, so thank you very much for listening, for your attention. I hope you have learned something. See you tomorrow. Have a nice rest of the afternoon. And yeah, thank you so much. Bye bye. See you.